Imagine a star once much larger than our sun, squeezed down to the size of Earth. This transformation is both awe-inspiring and mind-boggling, showcasing the incredible forces at play in our universe. That's a white dwarf, a bizarre and fascinating object that defies expectations. These remnants are the cores of stars that have exhausted their nuclear fuel and shed their outer layers. These stellar remnants pack the mass of our sun into a sphere roughly the size of Earth. It's a cosmic marvel how such a dense object can exist, with gravity so intense that it compresses matter to extreme levels. That means a teaspoonful of white dwarf material would weigh as much as a fully loaded cement truck. This density is almost unimaginable, yet it's a reality in the cosmos. White dwarfs are the final stage of life for most stars in the universe, including our own sun. When our sun reaches this stage, it will shed its outer layers and leave behind a dense core. They represent a cosmic graveyard of sorts, where the remnants of stellar cores continue to shine faintly for billions of years. These ancient objects are like time capsules, holding secrets of the universe's past. Their study provides valuable insights into the life and death of stars, as well as the ultimate fate of our own solar system. By understanding white dwarfs, we gain a deeper appreciation of the cosmic cycle of birth, life, and death. Stars are born, they live, and they die. For most stars, death isn't the end, it's a transformation, a transition to a new and fascinating stage of existence. Enter the white dwarf, the stellar equivalent of a phoenix rising from the ashes. When a star like our sun runs out of nuclear fuel, it can no longer support itself against the relentless crush of gravity. Its core collapses inward, while its outer layers expand outward, creating a spectacular cosmic spectacle, a red giant star. Eventually these outer layers drift away, leaving behind a hot, dense core, the white dwarf. The formation of a white dwarf is a dramatic cosmic event. It begins with a star like our sun, steadily fusing hydrogen into helium in its core. This nuclear fusion provides the outward pressure that keeps the star from collapsing under its own gravity. Over billions of years, the star gradually exhausts its hydrogen fuel. The core contracts and heats up, eventually becoming hot enough to fuse helium into heavier elements like carbon and oxygen. This process repeats, with the core contracting and heating further, until the star can no longer sustain fusion. At this point, the core collapses, triggering the star's transformation into a red giant, and eventually, a white dwarf. Section 4. Cosmic heavyweights tiny but mighty. White dwarfs are incredibly dense. Imagine squeezing all the mass of our sun, about 333,000 times the mass of Earth, into an object the size of our planet. That's the kind of density we're talking about. This extreme density comes from the way matter is packed inside a white dwarf. The electrons normally orbiting the atom's nucleus are squeezed incredibly close together. This electron degeneracy pressure prevents the white dwarf from collapsing further, even though it no longer generates energy through nuclear fusion. Section 5. Windows to the Cosmos. Unlocking stellar secrets. White dwarfs may seem like exotic objects, but they hold valuable clues about the evolution of stars and galaxies. These remnants of once vibrant stars are the final evolutionary state of stars not massive enough to end their lives in supernova explosions. By studying their properties like their temperatures, compositions, and masses, astronomers can learn about the life cycles of stars, from their birth in stellar nurseries to their eventual demise, the history of star formation in our galaxy, and how these processes have shaped the Milky Way over billions of years, and even the age of the universe itself. By examining the cooling rates of white dwarfs, scientists can estimate the time that has passed since these stars formed. Moreover, white dwarfs play crucial roles in certain types of supernova explosions. These cataclysmic events are not only spectacular, but also serve as important tools for measuring cosmic distances. These type Ia supernovae occur when a white dwarf in a binary system pulls material from its companion star. This process can lead to a dramatic increase in brightness. When the white dwarf accumulates enough mass, it can trigger a runaway nuclear explosion, releasing an immense amount of energy, briefly outshining an entire galaxy. These explosions are so bright that they can be observed across vast distances, providing a window into the far reaches of the universe. Section 6. A slow fade and a fiery end, the future of white dwarfs. While white dwarfs no longer generate energy through nuclear fusion, they are incredibly hot, with surface temperatures reaching tens of thousands of degrees. These stellar remnants are the cores of stars that have exhausted their nuclear fuel and shed their outer layers. Despite their small size, roughly comparable to Earth, they possess a mass similar to that of the Sun. Over billions of years, they slowly cool down, radiating away their stored heat into space. This gradual cooling process can take longer than the current age of the universe, meaning many white dwarfs are still in the early stages of this cooling journey. However, not all white dwarfs fade away quietly. Some have more dramatic destinies that can alter the course of their existence. Some experience a more dramatic fate. In certain conditions, a white dwarf can interact with a companion star in a binary system, leading to extraordinary events. As mentioned earlier, if a white dwarf is part of a binary system and accretes enough material from its companion, it can reach a critical mass and explode as a type Ia supernova. This process involves the white dwarf pulling in material from its companion star, gradually increasing in mass until it reaches a tipping point. These explosions are some of the most energetic events in the universe, releasing tremendous amounts of energy and scattering heavy elements into space. The resulting supernova can outshine entire galaxies for a brief period, leaving behind a rich legacy of elements that contribute to the formation of new stars and planets. The study of white dwarfs is a journey into the heart of stellar evolution, revealing the secrets of stellar death and the profound connections between the largest and smallest scales of the cosmos. By understanding these remnants, we gain insights into the life cycles of stars and the dynamic processes that shape our universe. These fascinating objects continue to surprise and amaze us, offering a glimpse into the intricate workings of the universe we live in. As we continue to study them, white dwarfs will undoubtedly reveal even more about the cosmos and our place within it.